Good afternoon, my name is Ridha Moosa, and I'll take you through our Kaggle house competition using linear regression. So, looking first at the data that has been compiled for us, it was compiled by Dean Lecoq, and it consisted of a train and test set data, which did differ in shape from each other. We can see that there were 43 categorical values, 37 numerical values for which were both ordinal and nominal. And sale price was our target variable. So the first thing we had to look at was some exploratory data analysis. And onto the next slide, we can see this is how we first prepared our data for EDA. So we kept our train and test data sets separately, deleted the IDs from both of them, but kept a test ID for submission purposes. And the first thing we had to look at was sale price. And the first thing we noticed was that it followed a log norm distribution. So when we were submitting, we had to log our data. And we used Seaborn to show the distribution plot. So from here, we can actually see how logging the data allowed our data to fit into a normal distribution. Now having a look at some of the missing data, our first initial idea was to drop the top 10 missing data points, but we did not receive a great score. So in the end, we kept those data because in real life, those features might be missing, and that is what could have influenced the sale price in some of the houses or apartments. Next, we had to look at some relationships between sale price and other features, and we looked at the top 10 of the numerical values, not categorical, just the numerical. And from this correlation map, we can see that overall quality and ground living area were naturally more important because quality does influence the sale price quite tremendously. Next, we had to look at how all the other variables correlated with each other, and it confirmed that quality was important, ground levels, and essentially the size of the plot was important. Some things were not as well correlated, like might not have a porch, might not be very well located in terms of the street, and not all the places had a pool. So what did we actually do to our data? So we could clean it up and put it into our models. So here are just some of the things that I can summarize that we did. So onto the next slide, I'll take you through the important ones that we did do. So as a preliminary transformation, we first filled our null values. So most of them we filled with a 0 or none. Some of them we filled with whatever central limit theorem that was applicable, like mode, median, or mean, depending on the data. And in some extreme cases, we had to go and manually input the missing data. Next, we grouped variables that were very closely related, like we created a total surface area, and then we had to look at transformations. And one of the important transformations that we needed to look at was neighborhood, because neighborhood had a lot of categories, and we needed to see how all the neighborhoods fitted into the sale price. The next thing we did was had a look at, was the quality important enough to be a fixer-upper? Essentially, was the house worth buying to fix up? Or was it too bad of a quality to market it at such a good price, or it's the price that was had a look at? That's where we created a scoring system so that we gave each quality of the house a score. Next, we replaced our integers with other values, and then we had to look at skew data. So assessing the skew data, we established an index of anything above the 75th percentile being skewed, and with that data, we box-cox transformed it. Compared to log norming it, box-cox was the go-to if log did not work. The last thing that we did with our data was we scaled it, which helped normalize the range of data. And this is when we split the data and test set to scale it. And we applied the robust scaler in SQL learning. Perfect. So some of the models, well, the most important model that we used was Lasso, which I'll show you on the next slide. Because Lasso was the best performing model that we had. The other ones that I won't go through were linear regression, ridge, and random tree forest. And we used root mean squared errors to assess the accuracy and cross-validation scores. So in terms of lasso will exclude those variables which are not very well correlated. And that's exactly how the L1 norm penalty works in machine learning. And we can see how well that data fits. Thank you very much, and I hope that was a good one.